So in this section, we're going to take a look at how we find definite integrals, and actually we're going to do indefinite integrals in the section for trig functions that have powers. So here's what we're going to look at first. So we're going to talk about sine and cosine. Those are the ones that come around the most. Agreed? Yeah. So sine and cosine. So if the power on sine is odd, okay, so if you have sine cubed, sine to the 5th, sine to the 57th, we're not going to have them that big, but if you did, that's going to be classified underneath guideline number 1. So if the sine on the if the power on the sine is an odd power, you save one of the signs. Okay, so you leave one of the signs as sine, and then everything else would then be an even power left over because there's an even number of them, and you turn all of those into cosine, and you do that using the fact that sine squared plus cosine squared equals 1. Right? That was the Pythagorean identity in trig. And you've got a sheet of trig identities that I gave you last time. We have a very similar process on number 2. If the power on cosine is odd, you do the same thing. You save one of the cosines for du, and then you change everything else into sines. Okay? Again, using that Pythagorean identity that sine squared plus cosine squared equals 1. And then the only case that we haven't encountered then is what if we don't have odd powers? Namely, what if all the powers are even? And if all of the powers are even, this set of these sets right here are not on that sheet that I gave you. So make sure you write these down properly. And they're in your book, of course, too. These are called power-reducing formulas. Okay? They allow you to take a power of sine or cosine, and they reduce the power, don't they? Sine squared turned into cosine, and cosine squared turned into cosine. Now, it changes it to be a double angle. But double angles are easy to work with in calculus because you can just let that be u and do a simple u substitution when you've got products of angles inside, like the 2x. Okay? So we actually turn those into an odd number of powers, and then we can go back to step number 2 because now we're dealing with an odd number of power of cosines. All right, so all of that sounds all well and good until you see what it looks like, because that's when it actually starts to all come together in your mind. So you're ready to take a look at one? Oh, you guys are still writing a couple of them. So let me pause for a sec. All right, so we're going to take a look at an example, and as we look at our examples, we're going to keep flipping back to that slide to determine which example guideline we're looking at. Okay, so here's my first one. We've got sine cubed of 2 theta square root of cosine 2 theta d theta. That's what we have, right? And we're supposed to integrate. And so looking back at those guidelines above, which guideline am I going to be using? The first one. Because I have a sine in this problem and its power is odd. It's sine cubed, right? Okay. So what this says I'm supposed to do is I'm supposed to save one of those signs, and then I'm supposed to change all the other signs that are still in the problem into cosines. So we're going to do that in a couple of steps just to give ourselves some, a chance to actually see this. And I'm going to move this up because I want to give myself some more room. All right, so come on. So taking a look at this, what this is telling me I need to do, ignore the double angle for now. That's not going to cause any problems like I mentioned earlier. But is that I'm going to rewrite this as sine of 2 theta. That's the one I want to keep. And then I'm going to write this as sine squared of 2 theta. And then I've got this square root cosine 2 theta business that I'm going to have to deal with in a little while. Okay, so are we good on that step? Yeah? All right, so that's half of what step number 1, guideline number 1 told me to do. It told me to leave one of the signs alone. And that's what I did, and I wrote out that I have 2 of them left right here. The other item that number told me to do is it told me that I need to take what I've just sort of put the curly braces around down here and turn them into cosines. And so I mentioned this before, but let me write it up here again. This is sine squared of theta plus cosine squared of theta equals 1, right? And I can take this formula and I can solve it for sine squared by moving the cosine squared to the other side. So it is equivalent to say that sine squared of theta is 1 minus cosine squared of theta. And that's the substitution that it was talking about, changing it into cosine squared. So we don't just get to sort of rewrite sine squared as cosine squared. We have to use trig identities to rewrite it as a correct value in terms of a cosine squared. So right now, I still have the sine squared, I'm sorry, not sine squared, sine 2 theta at the beginning. This piece right here is 1 minus cosine squared. And then I've got the square root of cosine 2 theta at the end, d theta.
What happened to the 2 theta?
Oh, it should have been a 2. I'm sorry. Yes, the angle stays the same. Thank you. So no matter what this angle is, it's just consistent throughout. Thank you, Emily. All right, everybody good so far? Okay. So the next thing I want to do is to recognize, and it told me that this was going to happen, is that these pieces right here, I'm not messing with them at all because that's going to be d theta in a moment. Okay, that's going to be my du value in this problem. But the other pieces I can combine. Okay, so the other pieces right here, in fact, whoops, I'm going to combine them at the beginning, and I'm going to move that sine 2 theta to the end with the d theta. So what I'm going to do is I'm going to actually distribute this right here. So the first one ends up being square root, or you know what, let's write the square root as a 1/2 power. Is that okay with everyone? So I'm going to write cosine of 2 theta to the 1/2, because that's what it's going to be multiplied by the 1 at the beginning, minus, and then I have a cosine 2 theta here. This is a power of 1/2 right here, and this one's a power of 2. So what happens when I have a power of 2 and a power of 1/2? What's my new power? Nope. It'll be 5/2. So we don't want to multiply, which is what you're thinking, Hannah. We're going to add. So this is back to some algebra ideas. This is like having a squared and a to the 1/2, and we add these together. This would be a to the 5/2. So we're adding the exponents. And then at the very end of all this, I have sine of 2 theta d theta. And I've dealt with the trig as long as I can stand it because I need u substitution. I know it because that's what guideline number 1 said, right? Because I'm going to need a du. So we're going to do that at this point. So u is going to be what? What do you think? Yeah, that's the cosine 2 theta. And one of the reasons why you should sort of be drawn to that idea is because you've got the cosine of 2 theta raised to a power, right? In a couple of locations. But when you have stuff raised to another power, that's sort of a product, not a product, but a chain rule going on, right? And chain rules draw us back into this idea of u substitution, just like product rules do. So I have a chain rule. And then what is the derivative of cosine 2 theta? Okay, so the negative sign comes from the cosine, right? The derivative of cosine is negative sine. This, and then the 2 theta stays the same. This 2 comes from the derivative of the 2 theta, right? The derivative of 2 theta is 2. Is that okay with everyone? Now, I don't have all those pieces in my problem, but I have most of it. I have the sine 2 theta. Oh, and I'm missing it still. D theta at the end. So this portion right here is in my problem, which means I can divide the other portion to the sides. This is negative 1/2 du equals sine of 2 theta d theta. Are we good? All right, so my antiderivative becomes the antiderivative of u to the 1/2 minus u to the 5/2. And all of that's times du with a negative 1/2 in front. Did I get that all right? I think so. Is that all right? Everybody? Going once, going twice? Okay, good. But we can integrate that, right? I didn't have any sines and cosines in it anymore. All right, so what's the antiderivative of u to the 1/2? Thank you, Hannah. Somebody else, what's the antiderivative of u to the 5/2? Does that look right, Kendra? Okay, great. And then plus c. Not quite done. There's going to be two things I'm going to do. One, I'm going to distribute that 1/2 through, but I also need to do what else?
Substitute back in.
I need to put them back in terms of x's, right? So let me do the distributing first just because it's kind of clean. So 1/2 times 2/3 is 1/3, negative 1/3 because I've got a negative. You do the 3/2. And then I've got a positive because it's negative 1/2 and 2/7, and what will it become? 1/2 times 2/7. 1/7, thank you. You do the 7/2. And then, just like Cameron had mentioned, the u's, they have to go back into x's. And the value we had was that, in fact, u was cosine 2 theta. So I'm going to have cosine of 2 theta to the 3/2 plus 1/7 cosine of 2 theta to the 7/2 plus c. Any questions on that one? Okay. We have one more example in this section before we have new directions, basically, of powers on sine and cosine. So I have cosine to the 4th of 3 alpha. If it really bothers you to continue problems in terms of alphas or thetas or betas or whatever the problem is, you change them all to x's. I'm okay with that. It doesn't bother me. I'm going to continue using alpha just because the problem started that way. But if you want to change them, it's okay. Which guideline is this? It's the third one. I only have one power. It's a power on cosine, I think. And it is even. So I'm stuck into the case number 3. Case number 3 says I'm going to make use of this formula, but if you take a look, my formula does not say cosine to the 4th. It says cosine squared, doesn't it? You can have 2 of those, that's right. So let me move over here. So what we're going to do is we're going to take this idea, and the thinking, kind of like what Cameron just said, is that this really is cosine squared of 3 alpha squared. Right? That's what it means to be a power of 4. It means something squared twice. So in other words, x squared squared is x to the 4th, isn't it? Okay, so the value that's inside now, the cosine squared 3 alpha, that portion of it matches what I had back on the very first slide, right? The one where it had the power reducing formula on it. So I can take that power reducing formula, and it said 1 plus cosine. And that cosine angle inside of that cosine actually was double the angle it started with. But my angle I'm starting with is 3 alpha. So my angle that I'm going to get right now is 6 alpha. It's supposed to be double the angle I started with. And all of this then is squared. Does everybody understand where the 6x came from? Okay. I'm going to square this, but before I actually square it, I'm going to recognize that if I squared the denominator, it would be a 1/4, right? Well, the denominator would be 4, but that would be a 1/4. So I don't want to deal with the fractions, really. I'm just going to pull the 1/4 to the front, and then let's square out the numerator. So remember, squaring out the numerator then as well, let me write this to the side, does not mean that we square each term. Okay? You giggle, but people still do it. It's just an oversight that you guys sort of don't think about every time. But this is actually what it means that I have on top, right? And I've got an integral here, and this becomes a 4. But in order to do that, I need to distribute the top out. In other words, FOIL, right? First terms, outer terms, inner terms, last terms, all that good stuff. So if I multiply 1 by 1, I get a 1. If I multiply the inside terms, I have cosine 6 alpha times 1. And if I multiply the outside terms, I have cosine 6 alpha times 1, which means I get 2 cosine 6 alphas. So plus 2 cosine 6 alpha. It's my inside and outside terms added together. And then the last terms, when I do cosine 6 alpha times cosine 6 alpha, well, that is cosine squared of 6 alpha. Now, we saw this happen before, and Nieder gave a really good suggestion that I sort of just blew right on past. I'm actually going to show it right here. Because I've got an integral of 3 different pieces, we're going to separate this out to 3 different integrals. And I'm actually going to write it that way with the 1/4 in front sort of ignored until the end. I need the integral of 1 d alpha plus 2 times the integral of cosine 6 alpha d alpha plus the integral of cosine squared of 6 alpha d alpha. Okay, so is everybody with me on that? That's a property of integrals you learned in Calc 1, that you can do that. And you use it all the time, you just don't always write down that you're using it. And I want to write it down here because I want you to recognize that the first piece, I can do that right now, right? The second piece, I can also do that right now. It's got a little bit of a U substitution, right, the angle, but that's not too much to work with. This piece right here is not yet written in a form that I can work with it. I need one more step of simplifying this in order to work with this piece. Is everybody with me? Okay, so I'm going to work with the first 2 pieces and go ahead and simplify them so I don't have to keep writing the integral, all right? So I've got a 1/4. What's the antiderivative of 1? Alpha, right, it's the variable. Plus I've got a 2. Now what's the antiderivative of cosine 6 alpha? So pretend for the moment it just said cosine of alpha or cosine of x. What's the antiderivative of cosine x?
Sine.
It's sine. So the cosine is a sine. The angle is still 6 alpha. All right, but I'm not going to show it because eventually you guys aren't going to need to see it anyway. But let me write it in. Oops, let me just try to do it in red. Let me write it in right here. If this were actually written out with U substitution, the U would be the 6 alpha. And what would du be? 6, right? The derivative of 6x is 6. D alpha. I don't have a 6 in the problem, so I divide the 6 to the other side, right? So whenever I'm dealing with a simple U substitution where it's just that angle, all that really ends up happening is that I'm dividing the entire value that I just got by the coefficient in the angle. And that always happens, okay? Now that's different in the last value because I've got cosine squared. I'm not dealing with that just yet. But when I have plain old sine cosine, and I've got that angle in there, I end up just dividing by the value in front of the angle. Okay, are we all with me? We're all good? All right, now I still need to do this last piece. And in order to do this last piece, I need to change this expression so that it doesn't have a power of 2. Which means I'm going to employ part 3, that guidelines number 3, again. Right? Over here. Whoops, went too far. This says that if I have a power on cosine that is even, I can use this formula, can't I? And I already did it once in this problem, so why not do it again, right? So I'm going to have 1 plus, I'm going to have cosine, I'm going to have double the angle and then divided by 2. Now, my angle currently is 6 alpha. So I've got 1 plus, and I'm supposed to double my angle, so what's my angle going to become? 12 alpha. And then this all gets divided by 2, right? And I've got d alpha here because I still have not taken any antiderivative. Hang on a second. Okay, so here's what we have to work with. And if you'd like, we can go ahead and distribute the 1/4 through here before, as we're taking our antiderivative, might as well. I have a 1/4 alpha. I have 2/6, which is 1/3, and I have 1/3 times 1/4, which is 1/12. So this is plus 1/12 sine of 6 alpha plus, and then I'm going to put this 1/2 in the front, so ignore the fact that it's got the 2 in the denominator. I'm pulling that 1/2 out. What is the antiderivative then of 1? That's alpha. And I need the antiderivative now of cosine of 12 alpha. So what's the antiderivative of cosine of 12 alpha? Sine of 12 alpha, and then what? Say it louder for me. Divided by 12, exactly. And I missed one piece along the way here, so let me put it in here. I should have a 1/4 also times this last integral, right? Yes? From the beginning? This is yes. We go up and down with our head. Works really well. Okay, because we're almost finished and you guys have other things to be occupying your time very shortly. So I have 1/4 alpha plus 1/12 sine of 6 alpha. What is 1/4 times 1/2? That would be 1/8. So I have plus 1/8 alpha. And I have that 1/8 now times the 1/12, that's the 12 in the denominator. So now we're really going to tax our brains and we're going to do 8 times 12. 96. Thank you, Hannah. So this is 1/96. Did you really do that in your head or did you grab a calculator? You did it in your head? Very good. Impressive. And then I have sine 12 alpha here. And I'm not quite finished. I missed it on this step, so I'll go back and put my plus c up there. And then, of course, I have a plus c down here. What's that? Yes, and that's one more step. Thank you. I can combine the alphas right here. They're the only ones I can combine, though, at least without using some trig identities. What's 1/4 plus 1/8? That is 3/8. So this is 3/8 alpha plus 1/12 sine 6 alpha plus 1/96 sine 12 alpha plus c. So if you ever wondered, when am I ever going to use trig again? This is an example right now today where you did, right? All right, so we're going to pause right there. There's 2 other things in this section that we will do next time. One of them is working with power-reducing formulas, or in essence, those same kind of ideas with tangent and secant. We don't actually do cosecant and cotangent because they're able to be changed into tangent and secant, so you don't see any reducing formulas in this section on those. And then we have one more piece at the very end of this section which doesn't do reducing, but it does combining different angle values. So we'll get those next time. All right, so if you would like, go ahead and start moving all of your papers to be put away. No notes, no nothing out for it. All you need is a pencil. And I actually sent these to the, oh, I told it to stop recording.